So the better explanation for this UDL is, if this is a seesaw, if there are actually three weights like this, which are actually now symmetrically placed, and here the weight number 1, weight number 2 and weight number 3, and these are actually placed symmetrically in such a way that it's completely balanced. Okay, now if you want to still keep this in balance, but you want to keep the load one, all these loads one above the other, how do you keep it? If you keep 1 and 2 on 3 like this, then it is shifting more distance, then it will start to go like this. If you are now keeping 2 and 3 on 1 like this, then it is actually covering less distance, then it will start going like this. So the better idea is to keep 1 on 2 and 3 here, so that it is still in balance, because one is trying to increase the distance, other is trying to decrease the distance, it gets balanced. So the concept is, wherever you got a UDL, you can imagine the whole UDL to be placed at the center. Okay, so don't replace the UDL by a point load, and that point load again you take it for shear force, and across this point load the shear force changes. Then you make shear force diagram completely wrong. Now you should imagine that the UDL is replaced by a point load only in your mind. Okay, don't replace this UDL with a point load anywhere in the diagram. Okay, this is about how to handle UDL. And similarly, you can handle UVL, uniformly varying load. So uniformly varying load is something like this, where for this uniformly varying load we give the intensity at the maximum point, maybe like 2 kilonewton for every meter is the maximum intensity, and they give the length here, maybe like 2 meters or something. Okay, now what is the moment that will balance this? Any idea? Now all this load will actually try to produce a clockwise moment. What is the moment that will balance this on the other side? Any idea? What kilonewton meter of anti-clockwise load will balance this out? Okay, now for that you have to understand one thing. First, from this point you should know what is this distance. Imagine this to be 1 meter. Imagine this to be 1 meter. Okay, then UVL is nothing but half of UDL, like this. Suppose if it is like this, suppose if the load is like this, then it is called as UDL. So UVL is half of UDL. Okay, so the total amount of UVL is half into base into height, which is actually 2 kilonewton per meter. Meter gets cancelled out. So the total value is half into 2, that is 1. So you are left with only 2 kilonewton. So the total UVL is 2 kilonewton, and we know that this 2 kilonewton, like UDL, it cannot be placed at the center because it is unsymmetric. Because it's 0 and it's maximum here, it will definitely shift to the side. You have to remember that in a triangle, the centroid of this triangle will be at a distance of 2/3 from this side and 1/3 from the base side. Wherever it is maximum, from that 1/3 distance you will have this load. So this 2 kilonewton has to be imagined that this 2 kilonewton will be placed at this point, which is actually at a distance of 2/3 of this 2 meter distance from this side and 1/3 of 2 meter distance from this side. But don't replace this with a point load. Imagine that this UVL is replaced with a point load only in your mind. Don't replace physically. Only by calculating, instead of UDL, you actually replace it with a point load exactly at the center. No? In the case of UVL, what you have to do? you have to take the total UVL. Total UVL is calculated as half into base into height. Where it should be placed? Should it be placed here? Should it be placed here? Where it should be placed? Exactly at the center? No, it should be placed at 1/3 from the larger side and 2/3 from the smaller side. Anything is okay. Like this, you should be able to solve numericals wherever UVL is given. Okay?